Welcome to the next in the series of our virtual coffee break webinar series. I'm Bob Farrell with RevSim.org. In just a minute, you're going to hear from Wolfgang Gintz of the Uber Cloud. You've also been here from time to time from Alan Chalker of the Ohio Supercomputer. The three of us are kind of collaborating with this webinar series, and we hope that you're finding it to be informative. If you've missed any of them, I invite you to visit RevSim.org. And there you'll find under RevSim Webinars a tab where you can view each of these very short webinars along with some others that we're always adding. RevSim.org. If you haven't visited by now, please do so. Take a quick look around. We're getting a lot of interest from visitors on the success stories page, along with how it works and resources, especially those areas where you kind of can see what, just like we're doing in this webinar series, some practical applications of democratizing simulation. RevSim is a community of lots of different organizations and people, sponsors and media members and so forth, solution providers, academia. There you'll see in this slide here just a real quick snapshot, and we hope that you'll join as well, because you're the most important part. You're the most important stakeholder. And so I invite you to take a closer look at RevSim.org. So with that, I'm going to turn things over to Wolfgang, and we'll get right into the case study.
Yeah, thank you very much, Bob. And this is Wolfgang Gintz from the Uber Cloud. And today we are looking at a case study about fast and cost-effective compressor map generation with computational fluid dynamics. The end user is ADS, Aerodynamics Solutions, CFD, and the application ran in the cloud on Amazon AWS. So the aim was to analyze and design centrifugal compressors to understand the performance characteristics of a compressor. Many complex CFD simulations must be performed for this analysis. And the use case is about understanding the effectiveness of cloud-based CFD simulations for analyzing, here in this case, the NASA CC3 compressor, which consists of an impeller, which you see on the right upper picture over there. The impeller with a splitter and a vent diffuser, and which is representative of a typical centrifugal compressor configuration. A compressor map is a graph which we want to generate here about how efficient a supercharger or a turbocharger is at creating pressure to move extra air into the engine. So the rule is simple: pushing more air into the engine will create more power, so to speak. Thank you. Next slide. And the software which Michael Nee from ADS CFD uses is called CloudWheel. It's a cloud-based turbomachinery CFD code based on the Reynolds average Navier-Stokes equations, and it is designed to take advantage of especially Amazon Web Services. More generally, it is cloud-enabled, so to speak. Designed for compressor and turbine aerodynamic design, this code, CloudWheel, allows users to provision CFD analysis capacity on demand and use it on a pay-as-you-go or pay-per-use basis. The code runs on AWS, as already mentioned, and it simplifies the process. So it's not only a CFD code, I should say. There is a lot of logistics around it to be able to process, automatically provisioning compute instances in AWS, loading the appropriate Amazon machine image, and configuring the firewall. It does it all from a user interface, or called also graphical workbench, running on the engineer's local computer, the workstation. And the workbench enables cases to be configured locally, like you can do mesh generation on your system or desktop, and then you transfer it securely to AWS, where the solver is then running. Okay. Yes, and here, we have some compressor maps which are generated with this computation fluid dynamics approach. You see two maps. One is showing efficiency, and the other is showing the pressure in mass flow units. And you see in each of these compressor maps, the simulation results for different scenarios here compared to the real physics, so to speak, which came out of real experiments. So the user begins by simulating an operating point at the design point condition for each of the 5 operating conditions. And the initial points are then examined for convergence prior to generating the rest of the map. Once validated, the workbench generates 39 operating points, which you can see here in the maps, the results of them, configured to run in parallel on 15 AWS instances. These are 8x large ones, called, these are the most powerful ones in AWS, especially for high-performance computing. And each of the instances is equipped with 2 Intel Xeon processors with each 16 cores and quite a bit of RAM and a 10 gigabit Ethernet interconnect. And the nice thing is all simulations completed within just a few hours. So again, as in many other similar case studies, the simulations in the cloud are much faster than what you can do at your desktop. And with that, I would like to invite you to join the Revolution in Simulation community. You see the registration link here, and you will see many more coffee break webinars from case studies from OSC, the Ohio Supercomputer Center, presented by Alan Chalker. And you can also go to the UberCloud website, register to the newsletter, and download a compendium of, the UberCloud CFD compendium, for example, which also contains this specific case study. And with that, we would like to thank you. And on behalf of Bob and Ellen, this was Wolfgang Gensch.